Okay. We are going to probably talk about all the rest of the topics in this lecture. Let's see how long it is. So topic 2C is on thermochemistry, and I'm going to have you guys share that on the board after you have time to review it and ask questions. So I'm not going to go over it because you would have seen exactly the same material in Chem 107 and 266. And the notation might be just a little bit different, but the ideas are the same. So I think we'll be able to share that, and in that way, you'll get any questions you have answered. So topic 2D is very new. It's about the idea of a state function will have an exact differential, and doesn't actually define what that means here, but I'll show you in a minute because it's going to do this over a couple of the focus, and I feel like it would have been better to actually define that more carefully through calculus, but I'll do that in a second. So figure on page 59, I can't remember what that is. Yeah, just showing you that state functions are independent of path. That's the important thing from that figure. So state functions also have exact differentials. I'll show you that in just a second. So if you look at the self-test 2D.1, it wants us on page 60, it wants us to calculate QW and delta U for an irreversible isothermal expansion of a perfect gas against constant pressure. So this is just a problem to start us thinking about how we're going to calculate things like internal energy change, and as we define the exact differential, it'll help us in different situations. So if it's a perfect gas, delta U equals 0 if it's isothermal. We talked about that early on, that a perfect gas, its internal energy doesn't change unless the temperature changes, because all you have is kinetic energy. You don't have any potential. So it doesn't matter if particles are far apart or close together, the internal energy will be the same. Therefore, work is going to be negative external pressure times dV, because it says it's irreversible against a constant pressure. And therefore, because delta U equals 0, work has to equal negative Q. So Q will be equal to pressure external times change in volume. So if we think about changes in internal energy, pressure, volume, and temperature are related to each other. So the internal energy is a function of pressure, volume, and temperature, but pressure is determined if you already know the volume and the temperature. So you can pick any of those two variables, and we're going to see that for internal energy, picking volume and temperature will be the most beneficial. So that will mean that any change in internal energy is going to have to be a function of how volume changes and temperature changes. And the proportionality constants are just going to be the partial derivative. So if we know how does internal energy change with volume holding temperature constant, and then I multiply that by how the volume changes, that will give me the total change in internal energy as a result of a volume changing. And then the same thing for temperature. If we multiply the partial derivative, that is a measure of how internal energy changes with temperature holding volume constant, if I multiply that by then how the temperature changes, will determine the quantity of internal energy change with a temperature change. This partial derivative is CV. This partial derivative is just given the name the internal pressure and pi t. But right here, I want to take a second just to really define what it means to say that this is an exact differential. So an exact differential for a state function means that it's independent of path. So let me just write this out. So on the right-hand side, what I'm showing is that I take the partial with respect to t holding volume constant. That's the first step in my changing internal energy. And then my second step is to change the volume holding temperature constant. So that's just one path from a TV, initial TV to a final TV. So change temperature first, then volume. And on the left-hand side, I'm saying I take a different path. I change volume first, and then I change temperature. If these two are equal, it means it's an exact differential. And it has to be true that if it's a state function, it will have an exact differential. So from calculus, we're going to see this is an amazing relationship. This is one of the times when I do think math, that we did not create math, that math is something we discovered, because this will show us all sorts of relationships as we go through the different focus on different thermodynamic properties that we would have never known otherwise. So when we look at this, this is called a total differential. The total change in internal energy. And if it's a state function, internal energy, then it will have an exact differential, where if I look at these two derivatives, they'll be related to each other when I take the second derivative. So after we set up this total differential, and I can put in my definitions for those two partial derivatives, looks like this. The internal pressure is equal to 0 for a perfect gas. We've said this a couple times now. Internal energy doesn't change with volume if temperature is constant. So that first term is 0. So for a perfect gas, we only have this term. So this term is going to be equal to 0. So how does internal energy change if we have a constant pressure? So let's look at our total differential from up here, but we've put in these definitions. And now I'm going to divide both sides by a change in temperature holding pressure constant. So that's just like dividing by X or anything else. It's a defined quantity. So when I do that, I get a measure on the left-hand side that will tell me how internal energy changes with temperature if pressure is held constant. So it's going to be pi t times divide this by dt constant p, divide this by dt constant p. And so change in t with a change in t is equal to 1. So you end up with this expression. And we define alpha. So most of these partial derivatives are given names just because they actually represent something. So this is the expansion coefficient defined. So how does something expand as a function of temperature? Kappa T is the isothermal compressibility. So how much does volume change if pressure changes when you carry it out isothermally? So we'll use those. They're not part of this definition. This focus is a little bit not as obvious why they're doing these things, but we'll need them later. So if we go back, we can put this in here because, yeah. So if we look at this, we ended up with pi t, dv dt constant p. So if we look up here, dv dt constant p is equal to alpha times v. So I can put alpha times v pi t cv. And it is going to be true that for a perfect gas, pi t is equal to 0, we said. And so that leads us to conclude that the change in internal energy with the change in temperature holding pressure constant is equal to CV, just like it was equal to, well, just like this was equal to CV. Our definition of CV. So doesn't matter how pressure and volume, one can be constant or the other. As long as you're changing temperature, you'll get the same heat capacity. So if we look at the self-test on page 62, 2D.2, they want us to derive an expression for kappa T for a perfect gas. So kappa T is negative 1 over volume. the partial derivative of volume with respect to pressure holding temperature constant. So the first thing I have to do is just take PV equals nRT and rearrange it for V so I can take that derivative. Now, if I want to take the derivative of the function of V with respect to P, I get all of these are constant because T is constant. I get nRT, and then the derivative of 1 over P with respect to P is negative P to the minus 2. So if I put that in for the derivative, then this negative cancels with this negative. Whoops, this negative cancels with this negative, and it becomes positive. And if I look at this, I can put in for volume. So volume is nRT over P. If I put that in here, you'll see that it simplifies to 1 over P. So simply put this in for 1 over V. So 1 over nRT/P means that nRTs will cancel and one of the P's will cancel. And so for a perfect gas, that kappa T, the isothermal compressibility, is just 1 over P. So now if we look at what we said was true for a perfect gas, how the heat capacities are related. So the heat capacities would be the definition of the heat capacity at constant pressure minus the heat capacity at constant volume. That should be a volume, not a P right there. Well, we can have it as a P because we proved here that they're equal to each other. So du dt constant P is equal to CV as well. So I'm going to do that because it will make the calculus easier. So for a perfect gas, H equals U plus PV equals U plus nRT, because nRT is equal to PV for a perfect gas. So if I put H in on the right-hand side when I'm taking the derivative, and here it's internal energy, that's going to be Cp minus Cv. So if I expand this, this is going to be du dt constant P plus dnRT dt constant P. So I get du dt constant P minus du dt constant P plus, if you take the derivative of nRT with respect to T, you get nR. And so you've just proven that the difference between the heat capacities is equal to nR for a perfect gas. For all other gases, we're going to look at this again in focus 3. We'll see that it's alpha squared temperature volume over kappa T. So this is an expression that you could then figure out what the difference is if you had a van der Waals equation of state or something like that. So how does enthalpy change? So we wrote a total differential for internal energy as a function of V and T. It's going to be better to use the variables P and T for enthalpy, and we'll see why that's true as we go on. So you could write the total change in enthalpy is equal to how it changes with pressure. So the proportionality constant, the partial derivative, times how much pressure changes, times how does it change with temperature. And so that looks exactly the same as our total differential for internal energy, except we've written enthalpy as a function of P and T. So you can skip the rest of topic 2D. We're not going to go into the details of how you'd measure some of these alpha kappas, different changes, but you can read it if you want. It's interesting, but it's not going to help us on our way to equilibrium. Okay, I think I'll just keep going. I only have 2 pages left. So this is topic 2E. This is adiabatic changes. So we had changes where we do no work. Now these are changes where we see no heat flowing in and out of the system. This is going to be super important when we define entropy and think about how entropy is a state function. So once again, this may seem abstract, but it's taking us where we need to go as we try to go to understanding equilibrium. So let's see, adiabatic changes. So for a perfect gas, when we look at our total differential, this first term is 0. So du is really just equal to Cv dt. So if Cv is constant, then delta U equals Q plus W equals W if it's adiabatic. So adiabatic means Q equals 0. So that means du equals dw. So we should be able to figure out some relationships here. So CV dt can be replaced for du, and work can be replaced with negative external pressure times dV if there's no additional work. Now we'll think about very specific situation, a perfect gas and reversible. So we're going to derive this relationship between T and V for a very specific situation. So always, when you look at your equations, make sure you're taking note on when they're valid. So on the right-hand side, I can take P external and replace it with the pressure of the gas. And the pressure of the gas, if it's a perfect gas, is negative nRT over V. So now I need to group the variables, because if you look at this, I can't integrate over V if T is also changing. But over on this side, it's measuring how temperature changes. So I'll take the T over here, keep the V over here, and then I'm going to integrate. So I'm going to divide both sides by T. So on the left-hand side, I'm integrating CV over T dt, and on the right-hand side, NR over V dV, and that 1 over X integral will do a lot is just ln. So you end up with ln or CV times the ratio, or the ln of the ratio of final temperature over initial, and on this side you get nr of the ratio. And so if you want to derive a more concise way to relate, so really what you want to see is how does temperature change with a volume change if I don't allow heat to flow in and out of my perfect gas. So I'm going to take the nr over to the left-hand side, and now I just have this. But then we also know that x times ln of y equals ln of y to the x. So I'm going to take the CV over nr out front and put it as an exponent. And now I'm ready to take the to raise e to both sides. And so when I do that, I find that the relationship between the temperature change and the volume change is a function of the heat capacity at constant volume for whatever gas you're talking about over nr. So when you think about how does then the pressure ratio change, so this equation is valid and easy to use if you know the volume change. But if temperature and volume are changing, then it's true that, I should write that here, pressure initial, volume initial over temperature initial equals pressure final, volume final over temperature final. And so in order to derive a relationship between pressures, it's a little more time intense. So I'll have you derive this part on the board in class, so that you can see that the pressure ratio is related to the volume ratio, but they're not just inverse. The volume ratio is raised to the gamma, and gamma is the heat capacity ratio, Cp over Cv. So that's it for focus 2, where we're introduced to the first law. In focus 3, we're going to be introduced to the second law, which is the most important law. You can't really understand the second law without the first law, though. So we have enough tools now that we should be able to understand entropy.